Okay, the next thing we're going to learn about with EXAFS Neo is how to do path optimization. So let's start our program up again. From the GUI folder, Python 3, exafs_GUI.py. And we're going to continue working with technetium hexachloride. So we will go through, select our data path. There's our input file, technetium cl6.xmu. For the output file, we're going to create a separate directory. So in a new folder, we'll make this path optimization. And save the output. We're going to choose the same FEFF directory that we've been working with the whole time. TCCL6 has all the paths in it. The population here is not going to change. The paths will be different now. So here we're going to make sure we check the path optimized box, so we do the path optimization. And we're going to look at the FEFF calculation, and in here there is a file, paths.dat. We're going to open up paths.dat, and we can see that there are 1, 2, 3, 4, 5, 6, 7, 8 paths. The first path with degeneracy 2, number of legs 2 and degeneracy 6, is a single scattering path. The remainder of all the other paths, so paths 2 through 8, are all multiple scattering paths with different values of R ranging from 2.35 to 7.05. So in this case, we're going to use all 8 paths in our initial optimization. So in our path list, I'm going to make that 1, 2, 3, 4, 5, 6, 7, and 8. We have to change our fitting region so it's correct. So for the technetium, it's 3.5 to 12.5. And background K weighting of 2 gives us the best results. We can verify that in the background plots, plot background and mu. See the K space data again and the R space data. In the outputs, we want to make sure we don't have create multiple input files. In fact, you would want to do the path optimization multiple times, and we'll show an example of that later. But for speed and showing how the path optimization works now, we're not going to create multiple input files. Come over to the analysis folder, and we can run. This will start the calculation. Because it is using 8 paths, it's going to take a significant amount of time. So we don't want to sit through the whole thing. It's probably going to take 9 to 10 seconds per generation here. So almost 10 seconds per generation. So it's going to go through the whole 100 of the first generation to optimize the parameters for the 8 paths. And we'll pick this back up when we get to that point. Okay, so now it has detected a steady state because it has optimized the set of parameters for all 8 paths. And it has determined that paths 1, 4, and 5 contribute strongly to the data set. So now it's going to go through and do the calculation only using paths 1, 4, and 5. And this will take us back to what we've been using in the past, paths 1, 4, and 5, so it's only taking 3 to 4 seconds per generation. But we'll pause again and come back when it is complete. Okay, we're coming up on the halfway point of the optimization of the three paths. One of the things you really want to think about, though, is the number of independent data points that exist in your data sets when you're doing the path optimization. Most people collect data in EXAFS with steps of about 0.05 inverse angstroms in k-space, so you're going to get about 20 points per every 1 unit of inverse angstroms in k-space. So when you're fitting in k-space, you don't typically have issues with the Nyquist limit. So here we're fitting 3 times 4 parameters, 12, with hundreds of data points. So we're fine in that case. In crystals, when you're worried about maybe 30, 40 paths, even that is usually fine for the path optimization. But where it gets tricky is when you've taken data sets that were quick scanned, for example, where not all the data points are independent. Usually you want to bin those first before you do the analysis to get an idea of how many truly independent points you actually have. So it's going through now. It's optimized E0 again and is now trying to do the final optimization, and we'll pick this up when it completes. Okay, there we have it. It's detected a steady state and it has completed. So the total time was 290 seconds, and the paths that were in the final optimization were paths 1, 4, and 5. And that is why we use paths 1, 4, and 5 to demonstrate most of the fits earlier, because when running with this path optimization, it shows that those are clearly the dominant paths. Okay, so when we come back, we see in our path optimization directory that we have output data, output optimized data, output optimized, and output. So to make this easier, it's good to create a new folder, output, and put the unoptimized output into that folder. That way you won't get confused with what you're analyzing. And then we can choose the analysis directory, path optimization, and it will analyze the optimized data. Now when we go here, we have to change the paths, our path list, so it includes the set of optimized data, which are paths 1, 4, and 5. Then I can come here and run the analysis. The analysis will complete with those 4 paths, and we can plot the data with the best fit in K and R space. You can plot the individual files as well, and we see the raw data, the genetic algorithm result, and the data from paths 1, 4, and 5. Again, we have a table that we can copy and paste into a LaTeX document, and we can see the results of the table with the paths that are involved and what the different individual fitting parameters are. Again, also saved in the file are the files that are necessary to create a plot in Igor Pro as well. So that all exists as well. But this allows us to determine which paths strongly contribute. So if I were doing an experiment where I was watching something convert and form TCCL6, and I was trying to analyze the data as a function of time, I would make sure I only wanted to use these 3 paths in the data, because these are the ones that contribute strongly to the TCCL6.